So we will start with the last topic, that is a finite word length. So what is the effect of finite word length? We will be discussing this into this coming two lectures. So basically, whenever we are going to implement any DSP or then any digital system by using a hardware or by using a software, basically in terms of software we are going to implement. Then to implement that software part, we should be considering the coefficients of the filter, and that coefficient should be designed such that designing will include the values in the form of bits. Basically, the bits are used to represent the coefficients of our filters. So in that representation, if we need to store a value that is 5, we will be having different bit representation based on the uh, available space, memory space. We will be dealing with the representations, so that yes, so that coefficients of the filter should be represented such that we should be utilizing the available memory space. Okay, so basically in the computers, the memory is in the form of registers, that is having different bit of registers we use based on the processor. Okay, so based on the number of bits or register can store, that much bit is available for storing a particular coefficient of a binary filter or any filter. Okay, the DSP filters. So these coefficients, if we are representing these coefficients in terms of 2 bits, okay, so these coefficients can have a maximum representation in terms of 2 bits. So there are 0, 0, 0, 1, 1, 0, 1, 1. They are the different possibilities that we will be using in the form of binary. And suppose we are having 3 bits, then we have possible values. These are 4 possible values are there. So in terms of 3 bit, if we are going to represent, it will be having total 8 possible representations. Okay, or suppose we need to represent a value that is 15, and if we are going to represent this 15 value in terms of 2-bit representation, okay, so that we cannot represent it, or we will be representing then only a maximum value 1 1 we can represent. But suppose instead of 2-bit we can have 3-bit, then the maximum value we can represent is 111, that will be 7 more closer to 15. And if we are going to represent 4-bit, it will be this. Okay, so this will be representing the 15. So like if we are going to have a representation, if we are representing by using 2 bits, it will be having maximum error. If we are going to represent in terms of 3-bit, it will be having even this value is 7, but it is around half of this, but it is closer to 15. By using 4-bit, we can have the better accuracy to represent. Okay, so this is how the number of bits or number of word length, whatever word length is there, that word length will be defining the quality of coefficients or the accuracy of that filter. So if we are having higher word length, we will be having better accuracy. Okay, so these are the different effects that can affect the performance of our DSP applications or DSP system. So these DSP systems uh, should be having the effect like finite word length effect. And what are these effects could be there? We will be dealing with this one by one. So basically in this we will see uh, two different effects. So one is truncation or rounding. So these are a truncation. So if we are going to represent 15 in terms of 2-bit, we have to truncate some of the values of this 15. So 15, if we are going to represent it, it will be, this is in terms of 4-bit, but instead of 4-bit we are having only 2-bit for representation. Then we have to truncate 2 of the values, okay, or we have to make the rounding off, okay, we have to remove this, only one is possible to represent, or we are going to represent it in terms of 3-bit, we have to drop, or we have to truncate it to 3-bit, that is 111 representation. Okay, so what is the effect of truncation and rounding off? We will be dealing with these. So basically it is, so here we will be dealing with the truncation and the rounding off problems, the effect that can be causing with respect to the word length of a digital filter, how the coefficients of a digital filter can be represented in terms of the finite number of bits, or what is the length of the word that will be causing these two errors. Okay, so the effect of this finite word length could be in terms of DSP of complete DSP applications, like the one is quantization effect in analog to digital conversions. So whenever we are going to convert an analog system, analog value to a digital value, there may be an effect called quantization effect. There are the different issues related to the finite word length. If we are having a finite word length, then what will be the problems or issues related to this finite word length? So this is quantization effect in analog to digital conversion. And product quantization and coefficient quantization, if we are going to uh, represent two product values, if we are product multiplying two values, and we are going to have the result, this result will be quantized to it, be assigned a value, binary value, so that may be having some product quantization error, or this coefficient itself can have a quantization error. Okay, so there is another problem, that is limit cycle. We will not be dealing with this basically. Okay, finite word length effect in fast Fourier transforms. So in fast Fourier transform calculations also, there are different coefficients that we use, and also we store the multiplication of the each stage's values. So basically we are seeing the type, basically the truncation and rounding of errors basically. Okay, so here in that we will be seeing the truncation and rounding of errors, and along with that we will be seeing the effect of quantization. We will also see the what is the effect of quantization. So these uh, two topics are basically in our course, so that two topics we will be dealing with. Okay, so starting with the rounding and truncation errors. Okay, so in case of rounding and truncation errors, it gets errors in terms of the magnitude of the value, whatever magnitude representation is there. So this magnitude representation will be having different number of bits. So in rounding and truncation errors, we will be basically seeing what is the effect of rounding a bit or a value. So if a value is written, 0101 is written, so if we are reducing this, making a rounding, that means we are going to remove one of the bit, or we are going to reduce this bit either 0 or 1, we will be getting the rounding of error. In case of truncation errors, so if any number is there that is represented in terms of 4-bit, but if we are going to reduce this representation instead of 4-bit, we are going to represent in terms of 3-bit, then this will be called the truncation. So in case of truncation, one bit will be completely removed. Okay, so there will be, instead of 4-bit, it will be represented in terms of 3-bit. Okay. So these type of representation of a number, that representation will be in terms of the representation of coefficients of a filter. So basically in digital signal processing, we will be dealing with the coefficients of the filter. Okay, so here rounding and truncation will be introducing some error. So we will see one by one, like how it is going to represent. Okay, these errors. So these errors could be represented in terms of different type of number system. So the numbers are, these are the decimal numbers. Okay, So these decimal numbers can be represented in terms of a sign bit number, sign magnitude representation, or in case of 2's complement representation. So what type of representation of a number is there? Based on that, there will be a different type of different values of errors possible. Okay, so we will see that if a particular number is there that is in terms of represented in terms of sign magnitude, then what will be the error in terms of rounding and truncation errors. And similarly, if it is represented in 2's complement, then what will be the rounding and truncation errors? We will be seeing that. Okay, so we have considered two numbers. Suppose this is the original number, that is x, that is represented in terms of different bits, and the most significant bit represents the sign bit, and all others are having up to l minus 1. So total l is the length of this x number. X is a number represented in terms of either of the number system, either sign or 2's complement representation. So this number is having a length that is l. Okay, l bit. Okay, so l bits are there into this x number. Similarly, we are having another number, or another number that is the quantized form of this number, that is represented as q of x, that is quantized form of x number. So in that quantized number, this number will be having the number of bits, and these number of bits is ranging from 0 to b minus 1. So basically it is having the representation up to b bits. Okay, so here this was l bits. So basically we are going to have the effect of rounding and truncation. So this is after quantization, this will be having b bits. So here b is considered to be always less than the l. Okay, so we are basically seeing one number we have taken x, that is having a length l. Now we are applying either rounding or truncation, and we are going to reduce the number of bits available into this x representation. So if x is the representation that is l bits, we are going to have another representation after quantization, that is q of x, that will be having a bit representation that is having b number of bits, and this b is always less than the l number of bits. Okay, so that will be representing q of x, will be representing in terms of truncation or different errors that can be there because of the finite word length. Okay, so here the errors basically represented in terms of epsilon value. Okay, so epsilon represents error, either we call it e, we can call it e also, but it is basically epsilon representing the error. Okay, so if it is truncation error, it will be represented by epsilon t. Okay, so we call it epsilon t, or if it is a rounding of error, we will be calling it epsilon r. Okay, so if it is truncation error, it will be this, rounding of error this. Okay, so we see like if quantization value, what is quantization value in terms of truncation, q of x will be having, if it is having b number of bits, or similarly what we can call it is, this is the value, like this is the representation, this is 5, and after quantizing, this value get a value that is 4. Okay, so what will be the 4 value? So this 4 value will be this complete the initial value along with the error. So this error could be positive or negative. So based on the error, so after adding error to the initial value, we will be getting the quantized value. Okay, so from there, if we find out the error, that will be given by quantized value minus the x. Okay, the original value. So this is how the error will be represented. Okay, so here we will be seeing there are truncation errors and rounding errors in sign magnitude and 2's complement magnitude one by one. Okay, so the first point is truncation error for sign magnitude representation. So in case of sign magnitude representation, we can see if it is 7, it will be for 4-bit representation, it will be 0 1 1 1. 6, it is 0 1 1 0. Okay, so if it is positive numbers, okay, so either it is in signed magnitude representation or it is in 2's complement representation, it will be same. Okay, but for the negative numbers, so negative numbers are represented like out of it is a 4-bit representation. So in this 4-bit representation, the last most significant bit will be representing your sign. Okay, so if it is signed magnitude representation, 0 will be having the 0 will be represented in terms of remaining 3 bits 0 0 0, and the most significant bit will be represented by 1 because this 1 will be representing the negative sign. So if it is 1, so 1 will be represented in terms of 0 0 1, and the sign for sign it is negative, it will be having a 1 at the MSB side. Similarly, okay, all the negative numbers will be having a 1 at the most significant bit. So this is in terms of sign magnitude representation, and all other bits will be this 2, it is there, it will be represented 2, this is 3, this is 4, 5, 6 and 7. So this is how sign magnitude representation will be there for different negative numbers. And similarly, if we are going to convert in terms of 2's complement representations, okay, the same will be converted to a 2's complement. Okay, so if we are going to convert it in terms of 2's complement, the always this will be the value 0 0 0, this 1 will be complemented, this will become 0. Okay, similarly here, if it is this representation, we will be converting it into the 2's complement. So this is the 2's complement representation, this is sign magnitude representation. So in terms of truncation, if we are going to have truncation in terms of sign magnitude representations, we will be having the effect like when input x, so input x is positive. Okay, so if input x is positive, suppose any positive numbers we are considering, so suppose 6 we have considered. Okay, so 6 we are representing in terms of 4-bit, it is 0 1 1 0. So this is your x value, and after truncation, what will be the value? So after truncation, the value will be q of x after truncation. This will be 0 1 1 because this least significant value will be removed. So this will be the value. So this value is less than this value, we call it, because it is representing 3 0 3 or 3, and this is representing your 6 value. So 3 is less than this, so that means we need to find out the error. So this error will be q of tx minus x. So this will be, this is 3 minus 6, so it will be a negative number. Okay, so this error will be negative. So here if x is positive, or initial value whatever we are considering, and if that x is positive, then the truncated result will be a reduced magnitude value, and that will be resulting in an error, truncation error, that will be negative. So this, in this case, the truncation error will be ranging from 0 to a value that is negative, and that value will be a negative, that will be 2 to the power minus b. This b is after the number of bits available after quantization, and then minus 2 to the power minus l, that is the length of this initial value. Okay, so this will be how the error in terms of truncation error that can be represented in terms of sign magnitude representations. Okay, so this is in case of the number x is positive. Similarly, if we are having a negative number, so if x is negative, so if we are considering any negative numbers, suppose we are considering this minus 4. So minus 4, so minus 4 is represented in terms of, minus 4 is represented like 1 1 0 0. Okay, so minus for 1 and 4 is this one. So this is minus 4. So this complete will be considered as x. So after quantization, the value will be 1 1 0. Okay, so this value is in the sign magnitude. Okay, so this is minus 4. Similarly, if you are representing this, so after quantization, this value will be minus, this will be 1, and these 2 bits will be represented the magnitude, so it will be 2. Okay, so this will be your 2. Okay, so this is After quantization it is -2. So -2 is higher than -4. Okay, so if we are going to represent the error, that will be -2 minus 4. Okay, so this will be giving you out sorry, this is minus. Okay, so this in terms of here, if we are finding the error, so this will be a higher magnitude minus the lower magnitude, that will be representing a positive value. Okay, so this positive value will be your error after truncation. In case of the value we have taken is negative, if x is negative, then the error is coming out to be a positive value. So in overall case, we can see the truncation error in case of signed magnitude representation will be having the range. So this truncation error will be having a range. In the positive, it will be having the maximum to the power minus b minus to the power minus l. Okay, so this is because of the quantization value. This is because of the actual value. Similarly, in terms of negative direction, it will be the truncation minus the negative, that will be having always a negative value. So it will be ranging from a negative to a positive value. So this truncation error in case of assigned magnitude will be having either in positive and negative both directions. Okay. Similarly, we will be seeing the truncation error in case of 2's complement representations. Okay. So in case of 2's complement representations, if we see, so this truncation error is coming out to be always a negative value. So either we take a positive value or we take a negative value, the same will be coming out to be. So okay, so if we are considering this or any number, suppose this is 2's complement number is there, so this is the number. So initially it was 4 in positive, but after truncation it will be 0 will be reduced, so it will be 2. Okay, so this is 2 minus 4 will be a negative error. Similarly, in case of a negative number, if this is the number, that is 1101. Okay, so this represents -3. Okay, so this represents -3. So after removing one value, we call it 1. If we are removing it, so it will be 110. So 110. So this will be represented in terms of this value, that is this is negative and this is complement. If we are making the complement, it will be 3. It will be making it complement, so it will be negative. This will be again uh, 0 and this is 1. Okay, so 10 again it will be. Okay, so that is minus 2 will be there. Okay, so this is how we will be making. So in terms of your 2's complement representations, the error that is coming out to be will be of the same, we can say the negative numbers, negative will be their magnitude will be negative. So always in that value, so in case of 2's complement representations, the truncation error will always be a negative value. Okay, that will be having this magnitude. Similarly, if we are going to deal with the rounding of error, so in round of errors, that we will be making sure in terms of sign magnitude and 2's complement representation. Here, the rounding of in case of rounding of errors, the effect of type of representation is not there. Okay, so what type of representations we are using, either sign magnitude representation or 2's complement representations, there is no effect of this type of representation in case of rounding off. So in case of rounding off of a binary number involves only the magnitude of the number. Okay, and it is independent of type of fixed point binary representation that we are dealing with. So the error due to the rounding off may be either positive or negative value, and the peak value of this magnitude will be 2 to the power minus b minus 2 to the power minus l divided by 2. So this will be the average of these two, like it is negative and positive, and its highest magnitude will be this, and minimum value will be the lower negative direction. Okay, so overall the error will be, this is 2 to the power minus b minus 2 to the power minus l. So this is the magnitude maximum value, and the range will be in between these two. So this is the range of the rounding of error in case of this either sign magnitude or 2's complementary representations. So the rounding of error is symmetrical about 0. So it is error. Rounding of error is symmetrical about 0 means it will be having the similar pattern in either positive direction or in the negative direction, and its range is this one, and also this is symmetrical about this means its mean value is also considered to be at 0. Okay, so its mean value will always be represented in terms of 0. So this is how the quantization will be taking place. Okay, so if we are quantization error in rounding and truncation, so in case of rounding and truncation, this is how the different errors will be taking place. So in terms of rounding, the quantization error will be represented in terms of the maximum value that we'll be dealing with is 2 to the power minus b will be the maximum error. Okay, so this error will be maximum 1, and in terms of the x value, we are going to see this value, it will be 2 to the power minus b by 2. It is half of this magnitude value. But in case of truncation of 2's complement and sign magnitude, it will be having this 2 to the power minus b, the highest and the lowest values. Okay, so this is 2 to the power minus b, and here it will be also 2 to the power minus b. The same mirror will be in terms of and the 2's complement also. So in the previous conditions that we have seen, if we are assuming like the precision is infinite, that means the number of bits into the x representation, x is the number that it is having of length of L, and this length is infinite. If we are considering this length is infinite, okay, then all the expressions of error that we have found it out, so 2 to the power minus L will be 2 to the power minus infinity, that will be equals to 0. So this 2 to the power minus L terms will become 0 because we are considering like it is having an infinite precision. That means it is having infinite precision means it is having infinite number of L or number of bits. Infinite number of bits are representing a number. So in that case, it will be having the highest precision. So in that case, the truncation error in sign magnitude and 2's complement representation and rounding of errors will be represented in terms of this. So in all the expressions, we have just removed the 2 to the power minus L terms because it will be equals to 0 if L is tending to infinity. Okay, so also the similar way like in truncation one we have considered the error. So similarly in terms of quantization also, the error will be the quantized one plus x plus epsilon value. Okay, so error will be in terms of epsilon value will be quantized one minus the x. So this is the generalized formula for the truncation along with the rounding of errors. So this is the probability density function of the different errors that are available. So if it is a rounding of error, in that case, this rounding of error will be having the probability density function. So probability density function will be having such that the complete probability should be 1, or we call it the area under this probability curve should be 1. Okay, so in that case, the range of error of rounding of error is ranging from minus 2 to the power minus b by 2. Basically we have seen here, so here that is minus 2 to the power minus b divided by 2. Okay, so the minimum error is not divided by 2. Similarly the maximum value is the error in case of rounding off, that is plus 2 to the power minus b divided by 2. Okay, so this is the range. If we find out the area, this complete area, it will be like this 2 will be the maximum value, this is this, so this length will be equal to 2 times 2 to the power minus b divided by 2. That means 2 to the power 2 to the power minus b. So this is the 2 to the power minus d. Okay, so whatever this is coming out to be 2 to the power 2 to the power minus b. So whatever having is we know like 2 to the power minus b is there, then whatever height should be there, so this is width, so this is height. So this height will be having, after multiplication, it will be having an area that is 1, because the probability, this is probability function. So this probability function should be having the complete probability will be 1. So here height will be considered to be 1 by 2 to the power minus b. So it is 2 to the power plus b. Okay, so this magnitude will be represented by 2 to the power b. Similarly, in case of the probability function in terms of signed magnitude truncation error. So in case of signed magnitude truncation error, the range is minus 2 to the power minus b to plus 2 to the power minus b. So this is the error range. So it is minus 2 to the power minus b to 2 to the power minus b. So the complete error range is coming out to be 2 times 2 to the power minus b. So this is 2 to the power minus b plus 1, or we can call it 2 to the power minus. Similarly, in terms of the 2's complement representation, this is the error. So its inverse will be the magnitude. So this is how the probability density function is represented. Okay, so usually we see like the rounding is used to perform quantization error. So rounding will be used to perform the quantization, because in the quantization uh, whatever the properties of rounding is there, that is a desirable properties, and the properties are like the error signal is due to the rounding is independent of type of binary representation. So what type of representations we are doing to represent a magnitude, the coefficient of a filter, it does not depend on the type of representation of a number. Okay, so that's why we will be dealing with the quantization. So quantization will be done such that we should be using the rounding as the method to do the quantization. And also the quantization, the rounding is basically represents a mean value that is 0. It is having a 0 mean value, and also it is having a lower variance. Lower variance means the variation between these the different two values while doing the rounding is having the lower value. So that's why we will be going for uh, performing rounding to quantize a given number. Okay, so that's why we will be dealing with a rounding technique or method for the quantization instead of truncation.